My name is Takeshi Terao. So today I'd like to talk about fast verification method for proving non-singularity of matrices. So we want to verify non-singularity for n by n matrix A using only floating point arithmetics. So if there exists R such that this inequality is satisfied, where I is the identity matrix, so then A is non-singular. So we introduce how to set R and first method computing an upper bound of this norm. So these are notations in this talk. So F is a set of floating point numbers and U is unit round off. Next, this notation indicates that all operations are evaluated using floating point arithmetic with rounding to the nearest and rounding downward and rounding upward. So next, absolute value of matrices defined as this example. So and this notation indicates that this inequality is satisfied element-wise. So for simplicity, we assume that neither overflow nor underflow occurs in this FF. So in this page, we introduce a computational cost. So for the matrix multiplication, so if we compute dense matrix times dense matrix, then computational cost is 2 times cubic of n flops. So these flops indicate floating point operations. So this is case of dense matrix times triangular matrix, and this is case of triangular matrices. So this is computational cost of LU decomposition, and this computational cost of inverse matrix. And this is case of triangular matrix, and this is dense matrix. So next, we introduced a simple verification method using MATLAB code. So we first set R as this. So this function computes approximate inverse matrix, and we switch the rounding mode to the rounding downward and compute x1 as this. Next, we switch the rounding mode to rounding upward, and we compute x2 as this. So this x is maximum number of x1 and x2. And finally, we compute maximum norm of x. So if this answer is less than 1, then A is non-singular. So computational cost of this function is 6 times cubic of n flops. So in this page, we define matrices. So A is n by n floating point matrix. Next, L hat and U hat are computed LU factor for PA. So and P is permutation matrix of LU decomposition. Finally, XL and XU are approximate inverse matrices of L hat and U hats. So after that, we introduce a first verification method. So Oishi and Lump set R as this and derive this inequality. So this E is one vector. So total cost of Oishi and Lump method is 4 over 3 times cubic of n flops. So this cost is 2 times of computational cost of LU decomposition. So recently, Inami Hata improved Oishi Lump method. So they set R and CU as this. So next, assume that VU is this one. So then this inequality is satisfied. So this alpha is constant depending on L hat, U hat, XL, and XU. So total cost of Minamihata method is 4 over 3 times cubic of n flops. So computational cost of Minamihata method and Oishi loop method is comparable. So in addition, upper bounds by Minamihata method is nearly half of that by Oishi loop method. Next, we introduce the other verification method. So let R be this. So then this inequality is satisfied. And we have two strategies to take the upper bound of this V. So one is the method using a priori error estimations. The other is method using rounding downward and upward. So one is Ozaki Ogita Oishi method. So let V be the vector V be this. So V is bounded by this one. So where XL is triangular and P is permutation matrix and A is dense matrix. Then cost of this calculation is cubic of n flops. Then total cost of Ozaki et al. Method is 7 over 3 times cubic of n flops. Next, we introduce the method using rounding downward and upward. So V is bounded by this one. Then cost of this calculation is 2 times cubic of n flops. And total cost of Ogita method is 10 over 3 times cubic of n flops. So these are first method and simple method and its computational cost. So in preceding studies, so R is defined by this one. So that so we set R is this. We set R as this. So like Minamihata method. So and derive the verification method with these flops. So we propose 4 new methods. So in this page, we introduce how to compute XL and XU. So let L hat and U hat be computed LU factors. So approximate inverse matrices of L hat and U hat are computed from these triangular systems. So XL and XU are approximate solution of these equations. Next, we introduce a priori error bounds. So this is a computed result of matrix multiplication is bounded by this one. Next, these are inequality for this real, so of LU decomposition and triangular systems. So then we set alpha L, alpha U, and delta A. So alpha L and alpha U are upper bounds of the Lisial for triangular systems, and delta A is Lisial for LU decomposition. So assume that alpha L and alpha U are less than 1. So then L hat and U hat are non-singular. So we propose that this inequality, so we will explain how to obtain upper bounds of XU times XL and delta A. So these are methods computing upper bounds. So method A and B compute upper bounds of xu times xl times v. So the cost of method A is order square of n flops, and method computational cost of method B is 1/2 cubic of n flops, because where xu and xl are triangular. So method C and D compute upper bounds of delta A times B. So computational cost of method C is order square of n flops, and cost of method D is cubic of n flops. So in this page, we summarize proposed methods. So we propose four verification methods. So these are methods for xu times xl, and this indicates the method for delta A. So this is computational cost. So after that, we introduce the numerical result. So the test matrix A is generated in MATLAB by this function. So where con is the expected condition number and n is the matrix size of A. So this mode is one of these values. So we first introduce a numerical result when mode is 1. So in this case, method TBC is better method compared to TAD. Remarks that computational cost of TAD is small compared to TAD. So this notation indicates that upper bounds of norm of RA minus I is greater than or equal to 1. So next, we introduce the numerical result when mode is 2. So if mode is 1, method TBC is better method. However, when mode is 2, method TAD can obtain better upper bounds. So next, we introduce a numerical result when its mode is 3. So in this case, there is a trade-off between computational cost and overestimation of upper bounds. Next, we introduce compare our method with preceding study. So when mode is 1, so method TBC is better method compared to Ozaki method. So because our method, computational cost of our method is smaller than Ozaki et al. Method. So, however, when mode is 2, so Ozaki et al. Method can obtain better upper bounds. Next, we introduce comparison with Okita-Oishi method and method TDD. So when mode is 1, our method can obtain better upper bounds. However, when mode is 2, Ogita-Oishi method can obtain better upper bounds. So this is conclusion. So we propose four verification methods setting R as this. So our method have advantage when mode is 1, 3, or 5. But if mode is 2 or 4, our method is not better than precision works. So these are references in this talk. So thank you very much for your attention.
Thank you. If you have any questions, it's time. Yes, please.
So I have a question. So for your verification methods, you're executing them using MATLAB on one computer, right?
MATLAB.
You have to speak slowly.
Yeah.
Also.
Sorry. Your verification methods, you implement them in MATLAB,
MATLAB.
right?
Yes.
And you execute them in one computer.
Yes.
Are your methods parallelizable?
Yes.
Can you parallelize them?
Yes.
Okay, that's both the question.
Also, we use just graph for data. So this is automatically parallelized.
Okay. Because then you can, implement them in FPGAs or whatever. In fast. Thank you.
Other question or remarks? So maybe I have one question. So as your so you propose a new upper bound of the R times A minus I to prove the regularity of the matrix A. This is what you propose. New method to prove that the matrix A is non-singular. This is what you propose.
Yes.
Yes. So my question is the following. Sometimes your method is better than the older one.
Yes.
Sometimes it does not work. As you numerical result shows that for mode, can you show me for mode 1 or mode 2 the last slide? Yes, for example this one, not the previous one. Yes, for mode 3, the method TBD is better.
TBD is better. However, TBD computational cost of TBD is high cost.
Yes, I can understand. But in this case, your method is able to prove that the matrix is non-singular, and this one does not work at all.
Yes.
Yes, this is what does it mean. So you're able to prove that the matrix is invertible in this case, but not in this case. Yes, that's it. So now my question is, why? Why does it work? Is it difficult to have a theoretical results that shows that in this case it's going to be always better? Because numerical results are nice, but I would like to have a theoretical proof that TBD is always better in mode 3.
Yes.
Do you think it's possible to have this kind of proof, or?
Yes, it is possible to prove that TBD is always better than others.
In this case, it's in mode 3, it's always better. This is not numerical results. You have a proof.
I think so. We can prove.
In the papers? Is the proof is in the papers, or?
I think so.
Maybe in your head.
Yeah.
Okay. Okay, thank you. Any other remark or questions? So I suggest we can.